Yep.
Got it.
Mm-hmm.
So go ahead and mention anything you guys want.
All right, we're live.
We're live, yeah. And, you know, Jerry wrote great notes, especially on how CCDs work.
Well, without the introduction, I just don't feel like it started.
Yeah.
Okay, so what do you want to start?
Episode,
What should we start with
33?
today?
If you want
I
to go to Hercules, the M13, that would
Good,
be a
that's
lot.
good. Let's do that. The
Yeah,
Great
'cause
Globular Cluster and Hercules.
Yeah, so say what you want to say, Jerry. I was just going to mention a little tidbit. Okay.
Okay. Oh, you're not going to mention the tidbit first.
I need the picture you sent, I think.
Okay. So in the constellation of Hercules, which is up in the evening nowadays, is
Low in the west.
Yeah.
What's that?
It's low in the west.
Low in the west, but still in the dark sky.
Yeah.
Yeah. So it's up in the evening.
Yeah.
Is the Great Globular Cluster in Hercules, called M13, Messier's 13th object. It is quite a nice object for amateurs. This is the finder chart for it. And you see on the trapezoidal shaped keystone, as it's called, for that part of the constellation, which is easy to see in the sky, then it's 2/3 of the way up between these two stars on one side of the trapezoid, or the trapezoid, and it's on the side that is opposite to the easy to find Lyra constellation, or what is that?
The bright star Vega there.
Yeah,
Vega.
but when stars make a pattern,
The summer triangle,
asterism.
asterism.
Yeah,
Asterism.
so it's on the opposite side of the keystone from the asterism of Lyra. So it's
And if you're
very
looking-
easy to find.
If you're looking west to look at this tonight, think of rotating this diagram 90 degrees clockwise, because
Yeah.
M13 will be down under Vega.
Okay. But that's okay. It's still on the opposite side of the trapezium, or the trapezoid,
The keystone, yeah.
not the trapezium. Oh, my spoonerisms are going to ruin me tonight. And then it's a very, if you go down to the next picture, Tom, this is what it looks like typically. If you kind of squint at it, this is what, to sort of lose the sharpness of the image. This is a picture taken in an amateur telescope. You can see the galaxy in the background up there to the right
Yep.
there.
That
which
was
is-
Jerry, that was going to be my comment.
Oh,
Yeah, I was just going to say that when I show this object through the 8-inch at Westmont, okay, clearly the stars just come screaming out of the M13, you know, the globular cluster. But this galaxy up here to the right of it, and so that galaxy is about this is a wide field view. That galaxy is about 1/2 of a degree away from the globular cluster.
yeah.
It's called NGC.
Oh, we lost you, Tom.
Okay. The virus is creeping up through our crew.
Yeah, I think it's NGC 6207.
Okay. So we'll let Tom join us as he can. This is taken with a small amateur telescope, probably a 6 or 8 inch or something like that. Wide field of view, as Tom points out, about a degree across. And if you squint at it a little bit, that's the visual impression of it you get, is a fuzzball. But this is probably a 10 or 15 minute exposure.
And also you can see these two bright stars on either side flanking it. Those show up really well in binoculars.
Yeah.
So you see those two bright stars, and then you see the fuzzball between them.
And he's got the imager has nice color here, orange for one star and white blue for the other. So that we know the orange star, its surface temperature is about 5 to 8,000 degrees Kelvin. And the blue star down here is probably around 40 to 60 degrees Kelvin. So it's a hot star. Now, if you go down to the next picture, Tom.
Hold on for a second. Let Tom back in here. Got to admit him. You know, pop up the other picture.
Welcome back.
Be connecting to audio still.
Okay. Okay, well, anyway, this is the core of M16 taken by the Hubble Space Telescope. And we have one of our members, I got out of the astronomy magazine that this galaxy, this globular cluster has more than 100,000 stars in it. And it's so dense that in some cases, stars in the clusters actually collide with each other and create younger looking stars called blue stragglers. So those are the blue stars in there. The other stars, the more yellowish and whitish ones, are very old stars and billions of years old. I know we have a diversity of opinion in the club about how many stars there are in this globular. I stick with the astronomy magazines over 100,000, which takes in everything else. One magazine claims it's 200,000, and then I've heard several people claim it's over 1 million. So if you want, we can start counting them.
Yeah.
Come to our own conclusion.
And Tim Robert always tells people at outreaches that, it's hard to come up with a number because they hire people at minimum wage to count the stars, and when it goes from night to night, they keep losing track of where they were.
Yeah. Okay. So anyway,
Wikipedia is saying several 100,000 stars.
Yeah. Okay. So we have over 100,000 to several 100,000. So that's in agreement. So
it's interesting about the blue straggler. I thought that was interesting.
Yeah, that's where they land on the Hertzsprung-Russell diagram. But the thing is that these globular clusters are different than other clusters that we've talked about recently, the open clusters. In the open cluster, it's a very early stage in the start of stellar lifetimes. They first form out of a cloud of gas and dust, and then the gas and dust gets blown away as the stars turn on. And so you have all these stars that are very young stars. This happened about 5 billion years ago to our sun. And I think it was 5 billion. Yeah, 5 billion. And but globular clusters are different. They've been around for a very long time. And they contain very old stars. They're held together gravitationally. While an open cluster gradually spreads out, they are not gravitationally bound to each other strongly. But the globular cluster, they retain their sphericity for a very long time. They do get tidally torn apart slowly by the fact that they're orbiting the galaxies like the Milky Way. So,
and that's interesting because as they orbit and they lose some of those stars, they also they contract. So they lose some stars, but they get denser. And then those stars interact with each other and can toss others out. And the same thing happens. They condense and they get denser and denser.
Right. But because they were made out of old stars, and yet there's hot blue young stars in it, that is a result not of having been made recently, but from a cloud, but having been made recently through a collision of older stars, which then make what appears to be a younger star. So,
and they're generally low metallicity stars because they're low mass and very old.
Right.
And they're not a good place to look for planets because they don't have a lot of the heavier elements.
Mm-hmm. But I believe they have found a planet in some of these clusters or near them.
Yeah, they found one, especially that's orbiting a pulsar in one of the globulars.
Oh yes, that's right. Yeah. So the role of the origin of globular clusters is not clear. It's still a topic of research. They do orbit they are surrounding the Milky Way, but they surround it in a cloud. So they would be, to make an analogy, they would be the Oort cloud of the galaxy, whereas the rest of the galaxy has collapsed into a disk, but the globular clusters have not for some reason. They're very interesting. They're nice objects to look for. When I was in Australia one year, we could see one called 47 Tucana with the naked eye, and you couldn't see that it was a globular cluster, but you could see that it was a fuzzy star. So anyway, that's my take on M13. Anyone else?
So what's the closest globular cluster to us? Do you know, Chuck?
M4 is the closest of the Messier objects. It's only like 4 4,000 light years away, something like that. I mean, it's a pretty small number
Okay.
compared to the other
So
globulars.
Jerry mentioned 47 Tucanae. This one right here.
Yeah. Yeah, it's pretty spectacular. That one and Omega Centauri. Omega Centauri looks like it might be the core of a smaller galaxy we've gobbled up.
That's one possibility for the origin of these globular clusters, is that we've had a lot of small galaxies orbiting us that have been slowly torn apart, except for the last core globular set of stars.
Have you heard of this one? It says Dijorsky's number one, or Dijorsky 1 stars. Metal poor. I guess that must be a globular cluster of some sort.
It kind of looks globular-y.
Yeah.
It's a weird
Could
name.
be.
Or at least very old, but low mass
Yeah.
stars.
Mhm. And because they're very old, they haven't gone through nuclear or supernova stage, and they haven't generated a lot of heavier but rarer metals. Remember the periodic table from last week? Okay, how about the moon tonight? Or actually, this will be Wednesday, but this picture was taken by a friend of mine, Daryl Metzger, here in town, as he was trying his new camera. He got a Canon EOS R5, which I think is the mirrorless camera. Is that right?
I don't know.
Okay. So anyway, he just didn't know how to release the shutter. So he looked around and found the new menu to release it and got this picture. It was low in the sky, you can tell, because there's a slightly red ring around the top of the picture and a slightly blue greenish ring around the bottom of the picture, right at the edge. Very faint. That's nothing wrong with any of his equipment. That's atmospheric refraction. So it was probably lower in the sky than straight overhead, would be my guess. Now he'll call in and correct me. But
and it's flipped. It's flipped top to bottom.
Yes. Yeah. And that leads us into the next thing, which is the same picture we saw last week of this region of Aristoteles on the moon. And this was put up there because it's about a week later. And so you can see how the shadows have changed, revealing more information, more craters. But key among it is one of my favorite features is the Alpine Valley, which Chuck pointed out last time. But we have more on the Alpine Valley this week. Down there, you'll see a picture of it close up. And this is used as back when I started out in the 60s doing amateur astronomy, this was used as a measure of the resolving power of your amateur-made telescope, whether you could resolve the rill in the central region of the valley or not. So it's obviously you're looking at the larger amateur telescopes, but the rill is, I don't know what the origin of it is. It could be a collapsed lava tube, or it could be a fault line. It's unlikely to be running water left over for like Mars rills, but we'll see. Do you have anything to say on that, Chuck?
No, it's just a really interesting feature.
Yeah.
It looks like something just plowed right through the mountains, But here, this makes it look more like a volcanic feature.
It does.
It says at Wikipedia, it says that the valley, most likely, this valley is a graben, which was subsequently flooded with magma from the seas, the mares. However, the valley could have been formed by stress fractures due to expansion of the mantle or contraction after solidification of the regolith.
Yeah, that's just what I said, but in more technical terms. Anyway, you can see it is quite a challenging feature there. It's 3/4 of a kilometer to 1 kilometer in width, typically along there.
That's like half a mile.
Yeah. So this also will show you why we can't see the lunar rovers from Earth.
Yeah.
So Jerry, there's numbers. The numbers on the top are like, half a kilometer to 1 kilometer.
Yeah.
The numbers on the bottom, well, then they say kilometers, but then they say meters.
So yeah, that's the depth.
That's the depth.
So that's talking about the whole valley, or is it just talking about that
No,
little thin river?
Just the point where the arrowhead touches the thin river. It's discussing just the thin river.
Wow.
So now we've surveyed the moon very extensively. There are 3D maps of it. So we have heights and elevations on virtually everything you can think of on the moon. It's very well mapped. So, and among that is that we have the depth of that rill. And
that's amazing that a kilometer is that narrow on the moon. I would think a kilometer would look bigger on a moon, but oh well.
Depends on how close you are to it.
Yeah.
And what size scope you have. Tom's not there. I was going to ask him if he's ever looked at this through his, 23-inch at the Westmont College? No.
24-inch.
24-inch. Okay. I don't know why I got an odd number there. Now, later this week, we're going to have a meteor shower on Thursday. This wonderful finder chart from the magazine shows the radiant in Orion. This is early in the morning, low on the horizon, but looking southwest as it's about to set. So it is going to be conflicted with the full moon, so don't expect a dramatic look at these things. You're only going to see the very brightest ones.
But the nice thing is, in your write-up, you mentioned that that M13 was first seen by Edmund Halley.
Yeah.
Okay. And these meteors here in the Orionid shower are pieces of Halley's comet.
Oh, okay.
Just to connect the two.
So is there any connection that you know of between the brightness or the population of this meteor shower and the return of the comet?
I don't know. I haven't heard of any increase in the zenith rate, but
it's probably
it does have a fair number of fireballs. It is okay. It can be very nice.
So it's worth getting up for in the morning to see this then, maybe.
Yeah. Well, yeah. I don't think you have to go quite till 6 a.m., but yeah, around midnight would be good.
Yeah. The next one is that there was a near miss in Canada in the last week.
Yes.
Where a lady got a very expensive gift given to her by the gods, where a meteorite crashed through her roof and her ceiling and came to rest on the bed next to her as she was sleeping there.
This isn't an image of that meteorite, however.
Oh, wasn't it?
No. This one is aerodynamically shaped. The one she had was more just a lump.
Oh.
And it was very black. It looks like it might be a high carbon content chondrite.
So why did they show that picture?
It said Scientific American and it had the caption under it. So I guess I got a little happy and assumed that it was the meteor.
Yeah, see, you can see pictures of the lady holding it here, or somebody holding it. You can see it's very dark and just rock shaped, not that aerodynamically shaped one.
Yeah. Okay. Oh, there it is. Yeah.
So Chuck, what do you think?
Yeah, that
what
doesn't
type
look
of
like
meteorite is that?
They said it was a chondrite, and you can see they've got actual pictures of it down below. You can see the chondritic structure. Yeah. It doesn't look quite as dark. I guess that must just be the fusion crust that looks really dark.
But what is the one they still show the picture I grabbed up there?
That's just a generic meteorite picture. I think that might be the Old Woman meteorite or one of those. It has a shield shape.
Okay, so a Scientific American editor grabbed the first one he saw.
Yeah. And the story I read on this impact was the lady heard this bang and woke up and she was covered with plaster dust, but she didn't find the meteorite initially. So she called the police, and the police showed up and they realized that there was construction going on nearby. And they said, they're probably using dynamite and you got a rock that got thrown up. So they went over to the construction site and they started talking to the people. They said, hey, you've been doing any blasting lately? And they said, no. And they said, well, this rock fell through this lady's house. And they went, oh, well, we did see this meteor. So they went back and they started looking and they found this under the pillow, like another pillow that she had on her bed.
And that they all said they saw the meteorite come down while they were hiding the dynamite sticks from the police. Okay.
And they were asking her if she wanted to sell it or if she, what she was going to do with it. And she said, well, when the scientists are through doing their examination of it, I want it back. That's my lucky rock.
Yeah.
Yeah, I heard that they priced it like $50,000 to $100,000. So
Yeah. Especially because it hit a house. Apparently they go up in value when they have this story with them.
They're called hammers when they hit something on the ground.
Uh-huh.
And there was a fall a couple of years ago in Chicago where pieces ended up on roofs, and one piece hit a fire hydrant and had some yellow paint on it from the fire hydrant. So that one was worth a lot more because you could prove that it actually whacked something.
Yeah.
I think it must have woken her up.
Yeah, it did.
Okay, so I was going to start a short brief, but as I write a thing on how your cameras work to take pictures, and I've started doing that, and I was going to kind of stall this off till next week because there's a picture I wanted to put in, but I'll try and talk through it. If you're ready for that, or do you want to go through the owl first?
We can finish with that. Sort of do all the observational stuff first.
Okay.
Okay. So you want to do the owl?
Yeah.
Okay, the owl. This is a favorite around Halloween. We always set up, if the weather's good, we set up telescopes in our driveway for trick-or-treaters. Although this year we'll probably just do it with a camera so they don't have to cluster around the telescope. And this is one of the kids' favorites around Halloween.
Uh-huh. Okay, let's go back to the picture you just came off of, the Finder chart. Thank you. Now this one is from my planetarium software, the Sky 6. And the W for Cassiopeia is obscured in this, but as Tom is running his cursor over it, it starts from the white star at the upper right down through, I think it's navy for the orange, then the white, then a yellowish, and down to a white again. These other lines that the planetarium program puts in, I find a little distracting. It's not the way I remember them. But the cursor, the double circle is on the Owl Nebula. M76 is in the neighborhood, and far off to the right for orientation, you can see the Andromeda Galaxy over there. So,
well, not the galaxy, just the tip of the Andromeda constellation.
No, but if you zoom out, you can see the galaxy.
Really? Okay, hold on. Sorry.
I think that's it.
Oh, yeah, you're right. Sorry.
Yeah. And these squares up there, the white squares are informational. One shows the time and the date when this was made, which doesn't really matter. It's roughly this season. And the other one down there gives the information on the object, NGC 457. Or is that, 457.
So how do they rate the magnitude on something like this?
They estimate, they do a photometric estimation of the total light being received from the object. So for example, if you look at M33, which is a particularly faint, but not that hard to find galaxy, it's magnitude 8. But in your telescope, it's not magnitude 8. It's spread out over a fairly large area, about the size of the full moon. And so it's magnitude 8 spread way out. So it's actually a fairly faint object. So when you get the magnitude of these things, it can be quite misleading. Yeah. Okay, now the close-up view of it. Now, the two brightest stars up there are not part of the cluster. They are interlopers in front of the cluster.
And they're kind of oversaturated in this image because one's blue and one's kind of yellowish.
Yeah. So,
and those are the eyes of the owl, and then you can see its wings extending off to either side and the tail down at the bottom, or the feet.
Even when I squint, I'm hard pressed to see an owl. There's another object called the Owl Nebula, which is a planetary nebula, and that does look like an owl.
An owl's face, yeah.
An owl face. It looks like a round face with two round eyes in it. So this one, I would say, kind of looks like, to me, it's kind of a beetle with claws out front and butterfly wings, but owl
Well,
doesn't do it for me.
another one I've heard on this one is it's an F-18 on afterburner. So you got a twin engine jet. The nose is down in the lower right.
Yeah.
And then the engines on afterburner are up top, top left, and then the wings are
Uh-huh. Okay,
sticking
that
out.
amateur is a little too close to his other hobby.
Yeah.
So anyway, okay,
Well,
nice objects.
and that's
Now,
fairly far away. That's like 10,000 light years away,
yeah,
Really? Wow.
out towards the edge of the galaxy.
now you've moved down to Abell 4, which is a planetary nebula. It claims to be one of the brightest planetaries at magnitude 14.8. I'm not so sure about that because the Ring Nebula is brighter.
8 or 9, yeah.
So I think they're talking about absolute brightness, like if you were there on the scene. It shows up real nice in an O3 filter. All of these do because they're very rich in ionized oxygen. The this
Jerry, can I ask you, how does an O3 filter work to make it show better? What's going on there?
works pretty good.
Now,
The
It's
O3,
passing only the wavelengths from ionized oxygen.
so
right.
the blue comes through.
yeah, it's a spike filter. It cuts out everything except that one wavelength, just like the H alpha only shows you the hydrogen alpha line in red. So, but the O3, these things are dominated by ionized oxygen. So all planetary nebulas are very enhanced from the background. So if you look in your telescope and you have an O3 filter in your hand, you can put it over your eye like a monocle. And I have a story about that. But you can put it over your eye and all the background becomes super black. The stars all dim down, but the planetary stays, it only goes down a little bit in brightness. And what it does is increases the contrast between the planetary and the background. So it's quite dramatic. You can pick it out if you can't find it, a planetary in a field, because sometimes at low power, these planetaries are very small. This one, I think, is only 22 seconds of an arc in diameter. So if you were to look at it in your low power eyepiece, say a 27 millimeter wide field eyepiece, you would not be able to pick it out from the stars. But if you put that O3 filter in front of your eye, all of a sudden, that'll be the only star left that's bright. So it's a good way to find them.
It's called blinking.
Yeah. Yeah, you can move it in and out.
Yeah.
Some telescopes, especially Dobbs, have a slider just inside the tube that goes in front of the eyepiece holder, and it has several different filters, and you can slide this thing up and down to look at the different colors. I prefer the monocle technique, but if I'm going to look for a long time, you can screw the filter into the bottom of your eyepiece. Now, one of our members, Gary Peterson, and I were up at the KOA campground in Santa Margarita doing an outreach, and there was a lady there who wanted to look, and she couldn't find the planetary. So Gary put his O3 filter on the eyepiece for her, and she said, "I can't see anything." And when she stood back up, the filter had stuck to the makeup on her face.
Oh,
And so we were looking around for the eyepiece, and she knocked it off her face and it hit the ground, and it rolled across the ground, and Gary was chasing after it. And he resolved never to do public outreach again. And we spent some time cleaning his filter off.
That's like Joe with his 18-inch and an expensive Nagler eyepiece at one of the museum outreaches. There was a lady who was a teacher, I think at City College, but I'm not sure, who showed up, and she, you had to kind of get on a little step ladder to look through his eyepiece because it's such a big scope. And she looked, and then she turned to her students and she said, "You look right here," and she tapped on the eyepiece with a felt tip pen.
So Jerry, the name of this thing is Abell 4. Now,
Yeah.
Abell, I thought he had a bunch of groups of galaxies that was known for. They pick out all these weird groups of galaxies. Is that just the planetary nebula just happens to be in the
That was
middle of
another
this?
guy's catalog of unusual galaxies.
Well, that's ARP. That's Halton ARP.
Yeah,
But
ARP,
that's it.
Abell also cataloged clusters of galaxies. So
Okay.
he did some planetaries and he did also clusters of galaxies.
Yeah.
You
I guess
certainly
he
can
just
see-
did his faves.
Yeah.
There certainly is a lot of galaxies showing up in this picture.
Yes.
Now, this picture was captured on the internet from the Sloan Digital Sky Survey and processed by an amateur while using PixInsight and Photoshop by John Bozeman. And he posted it on Facebook. He's one of my Facebook friends. Okay. Now, how all this works? Go ahead.
Okay. I was going to say, yeah, you can see the central star there that's burped off its outer layers.
Yeah.
And it's real hot and it's giving off ultraviolet light, and that's what's making the gas fluoresce there. So the fluorescing oxygen is very greenish, maybe even greenish blue, and that's why you see this this nebula around the central star. And
that distorted orange lensy things is a lenticular galaxy in the background. It's not part of the nebula.
Yeah.
These go ahead.
For this star to puff off so much oxygen, did it go through? It must be a little heavier star, so it went past the carbon and started making oxygen. Then it ran out and puffed apart.
Yeah,
a little bit different, or
yeah.
But our sun will become a planetary, and it will show a galaxy, an oxygen-rich halo, also of some form.
Oh, so they all go through that stage of showing oxygen versus other. I see
it's
red and blue.
It's common in all planetary nebulas, and our sun is not dense enough to get past the planetary stage with a big explosion. It's just going to collapse and burp, as Chuck puts it. Now, on the ring nebula, you can see it's got a darker central region, and in my telescopes, you can't see, in my smaller telescopes that I use for outreach, you can't see the central star because I use a 5-inch refractor for outreach. The central star is magnitude 14. And this whole galaxy is supposed to be bright at magnitude 14. So you would get a nice picture of the central star of the ring nebula.
Yeah.
With the digital Sloan survey.
Yeah, when we use the Malin cam on our 4.7-inch or 5-inch on the ring nebula, you can see the central star.
Yeah.
I just see more red on the ring nebula.
Yeah,
but there is the blue in the middle.
Yeah, that's nitrogen for the red, and the sulfur is yellow. There's some pink from hydrogen. You get a nice mix on the ring nebula and on the dumbbell.
Yes, the dumbbell is very colorful when you image it. M27.
And we think the dumbbell is the same shape as the ring. The ring's also a dumbbell shape, but we're looking at it. It's like an hourglass, and we're looking at it at the bottom or the top of it. Whereas with the dumbbell, we're looking at it sideways.
Yeah, there are some very strange shapes, very interesting shapes to different planetary nebulas. There's things that look like long bugs, and there's things that look like two jets almost that flare out. Very interesting shapes.
Yeah, depending on the central star, whether it's a double or whether you have a strong magnetic field, you get all kinds of shapes.
Uh-huh.
That one's pretty intricate.
Uh-huh. Now that looks like an explosion. It looks like something from Star Wars special effects.
Here's some green, huh?
Yes.
Oh,
that's another Abell. Oh.
Where do you find this group?
This one, that will draw you in. The one that's at about 10 o'clock up there, that one looks like a shark's egg. No, in the next ring inside.
Well,
there.
Up above
that
the
one
ring,
looks to me like the shark's eggs that you find down here on our beaches. And there's up around about 1 o'clock, there's one with a real nice dark interior and a nice well-defined central star. As we get smaller and smaller, I don't see the Abell 4 down there. It's probably very small. Oh, this shows them in terms of their, not their apparent size, but their actual size. 4 light years apart. Okay. Okay.
Where are we going?
I guess we're out of everything else. We're going to go to the technical one. I was
All right.
worried it's a little too technical and I wanted to make it with more graphics for next year, but I'll try and get the point across. First of all, at the heart of every camera, this includes cell phone cameras and the expensive CCDs you buy, they all use a piece of silicon to absorb the light, the photons, and convert it into electrons. And the process I have up here that the photon emitted in the Andromeda Nebula over 1 million years ago travels throughout the hills and plains of space-time and goes right down the tube of your Newtonian astrograph and is finally stopped in the small volume of silicon that forms 1 pixel of an eventual image. This silicon focal plane is the heart of your camera, and it has a 2-step process in it to produce the photons that you can detect. First, step 1 is absorption of the photon by the material. So we're going to talk just about quantum absorption, where it produces an electron-hole pair, and that is the step 1 image down below, where it's got 2 greenish bands representing representing on the lower one, it represents the valence band, and on the upper one, it represents the conduction band in a solid piece of silicon. Now, the conduction band happens when you make a solid out of silicon and you push the atoms together, their electronic energy levels start overlapping, and that's not allowed by the Pauli exclusion principle. So the electron levels have to offset slightly. And when you get a whole slab of silicon together, 10 to the 23 elements, then you get 10 to the 23 orbitals that are very close to each other, and they form 10 to the 23 states in a band. And the 2 bands that are important for us here that do this are the conduction band and the valence band. The valence band, these electrons are still bound to the atom. They're the bonding band electrons. The electrons in the conduction band, the upper band, these electrons are free to move throughout the whole piece of silicon. They're not really attached to anything. If you apply an electric field to one side of it, all the electrons will run to the other side because they are repelled by the negative field, negative electrode. So that's how you get a current to go through a piece of silicon, is just apply a bias across it. But in this case, you see there's a little H and a nu there, and a wiggly line. That's a photon that's coming in. And if the photon has enough energy, it's going to hit the silicon and it's going to excite one of the valence band electrons up to the conduction band. And so you now have an electron-hole pair, and the hole can move. It moves one way under an electric field, and the electron moves the other way under an electric field. So what happens is you create in a neutral piece of silicon, if it just sits there and it's not in a camera, the light comes in, it creates an electron-hole pair. The electrons are negative, the holes are slightly positive, and so the electrons and the hole slowly are attached. They sort of orbit each other in a big Bohr orbit, shielded by the mass of other charged particles around. And then after their minority carrier lifetime, or their carrier lifetime, I should say, then they recombine and they either emit a phonon or a photon, and nothing was detected, even though you created the electron-hole pair. In order for it to work as a detector, you have to know when the electron-hole pair was created. So what you do is, the next picture down, it shows 2 pieces of silicon rammed together. One is a P-type silicon, that's on the left, and the other is an N-type silicon, that's on the right. And where they jam together, they have an excess of electrons on the left and an excess of holes on the left. Excuse me, an excess of electrons on the right, excess of holes on the left. And when they jam together, the electrons and holes fall into the other part, into the other material, until you build up an electric field inside the junction region that stops that process. So it stabilizes and it forms a depletion region. The key thing is that depletion region has an electric field across it. And so what you're looking at here is in equilibrium and nothing flows. But now if light hits an electron in the depletion region and excites it from the valence band to the conduction band, the electric field immediately separates it and sends it to opposite sides of the silicon. And of course, we have a wire connected through a meter on the outside. So we can now, in order to recombine when their lifetimes are up, they have to go through an external circuit to recombine, because the electric field we built in this internal to the material is preventing them from directly recombining with each other. So that's the key element of a detector. It's a two-step process. You have to form the electron hole pair, and then you have to, oh, the second thing is missing. Oh yeah, there it is. You have to form the electron hole pair, and then you have to collect the electron hole pair at the output. Now, what we have in the other chart, the greenish chart, absorption coefficient for silicon. Yeah, one more there. You can see that this is wavelength in the bottom line. That's 0.2 of a micron to over 1 micron, which is light that silicon can detect. The absorption coefficient is the absorption length. It's how thick of a piece of silicon you need in order to absorb most of the light. And the cutoff wavelength for silicon, direct bandgap silicon, is up at the top between 10 to the 6 and 10 to the 5. It's that arc that curves down, straight down. And then it starts meandering off to the right as it goes down. So as we go to longer wave, so that cutoff wavelength for silicon is 400 nanometers, but you still get good detection past that through an indirect bandgap interaction. So it's temperature dependent, and you can see that the red line is the absorption at room temperature, and the blue line is the absorption at minus 100 degrees. So you lose a little quantum efficiency for that part of the curve. But what this really means is that on the left, you can absorb all the light that you're going to get in, or essentially all of it, with a very short piece of silicon. So if you have a slab of silicon, the blue light comes in and it's going to get absorbed by the silicon right away. They're not all absorbed at the same place. The green light in the middle, between 10 to the 4 and 10 to the 3, that's going to get absorbed between 0.5 and 0.8. That's going to get absorbed roughly in the middle of the band, or the middle of the piece of silicon. And then the red light is going to go on down toward the into very short absorption lengths. So it's going to take a very, very big slab of silicon to absorb that light. So you don't get equal spectral response from these detectors. What you get,
Jerry,
yeah.
is this silicon? Is it doped in one way or another to?
Yeah, if you go down to the band gap, there are the two energy bands, the valence band and the conduction band. The oh no, I mean to the one that shows the depletion region on the bottom. The stuff on the right with the pluses in the orange and the green electrons around it.
Hold on, let's get up there.
Next
one
there. The stuff with the plus atomic cores there and the green electrons, that's doped N-type. It's got an excess of electrons. And the stuff on the other side, the XP, that's got negative cores and it's doped with extra holes. It's P-type material. So those are the two types of doping that you use in silicon. Silicon's a very robust material, so you can do ion implant to get your dopant materials into the material. In other materials like mercury cadmium telluride used for the IR, the material is very fragile. So the doping itself, just the fact that you disrupt the crystal is N-type. So any defect or damage is N-type. So it's really tricky to do implants in that. So the fact that there's not absorbed at the same depth means that you have this depletion region, and you got to make the depletion region at the right place in the material where you want to collect the most carriers of that color. Now at the surface, the blue stuff, the blue light is absorbed at the surface, but there's a lot of the surface states causes an enhanced recombination. So you lose a lot of signal there just because you're near a surface. On the other end, you lose a lot of signal because the silicon isn't thick enough. But in the middle, if you put your depletion region there, you get a spectrum like shown here for CCD sensitivity there. And you see it always peaks in roughly in the middle of the spectrum, around 620 or so nanometers. The blue end down here, the quantum efficiency is fairly low. It goes up, in this case, to about 85%, almost 90% at 660. And then it drops way down in the red as you get toward 1 micron, which is the near IR. These are different CCD, not CCD, but these are different pieces of silicon that put the depletion region, they're different thicknesses, and they put the depletion region in different regions to try and catch more of a certain carrier. You see the blue line in here, the depletion region was put near the surface. And so they're trying to do a blue enhance. They're trying to collect more blue light, but they're competing with the surface, which really has a very high recombination rate. And so this is the best they can do. And then in the middle, they're not collecting a lot. And of course, because the silicon doesn't have the depletion region spread out over the whole thing, they get very, very little red. The red line is one that's enhanced for red sensitivity. Usually when we do this, I believe hydrogen alpha is around 600. And so virtually everything that we do stops at around 740, 750. And that's where our stuff cuts off. As long as that's in a DLSR camera, because the glass doesn't focus all these wavelengths to a sharp focus. But in a CCD, you can get the really broad response that you get with the black line. Now, once you collect these carriers, the depletion region has let you send them out to each side of the thing. And if everybody's not still asleep, next week, I'll show you what we do with the electrons when we get them out. And I'll show you a graphic that explains this a little better. Actually, I think this may have boggled the Baron here, but we'll see. He can look at it in retrospect and ask comments next week. Okay, wake up. Tom, are you talking?
We can't hear you.
Tom, are you talking?
Oh, sorry.
Okay.
I had my microphone turned off.
I figured you were chewing gum, but yeah.
Thank you. Tim Crawford has some comments that he's made here. So I'll kind of work backwards here. He's curious about, is there any other element besides silicon that could be used? I think you kind of mentioned that about mercury, telluride, something.
There's a wide range of materials. Germanium can be used. Any semiconductor can be used. For the infrared, there's a very wide range because silicon and germanium don't go very far. For telecommunications, you use combinations of 3,5 materials, which are elements that form alloys from column 3 and column 5 of the periodic table. This is like indium arsenide, indium antimonide, gallium arsenide, things like that. For really long wavelengths, you use random substitutional alloys, which is 2,6 from the 2 and 6 column of the periodic table. Things like mercury cadmium telluride or lead tin telluride. Lead tin telluride was the first one used because it's easy, but it's very slow. It can't do fast response time. So all the far wavelength stuff is done with mercad telluride. Now, there are other ways of detecting photons too. I'm talking about the process of quantum absorption, where a photon comes in and it creates an electron hole pair. You can also isolate a piece of material, say silicon, and you can coat it with a black material, and you can let the light come in, get absorbed by the black material, and heat up the silicon wafer. And you measure that heat as an input signal. These are thermoelectric detectors. And there's another name for it too. But these can be made out of all sorts of things. And the key is when you do your processing is to make a freestanding wafer of silicon held up by a couple of spring-like ramps that go up to the plateau. You want it so there's no heat sinks, so that you can measure the temperature easily when it goes up and down, and you coat it with some kind of material that changes its resistance when the heat changes. And what we're talking about here is micro degrees, but they're very sensitive. They're very cheap to make. And a lot of the cameras that you see that people are using, you can even buy a camera adapter for your cell phone that takes infrared pictures in the long IR. I understand it runs about $200. It's fairly low resolution, but that's a thermoelectric detector like that, a heat detector. It's made by, what's that big, FLIR, made by FLIR.
So Jerry, what's the difference between heat and infrared?
Infrared is a wavelength, a spectral band of wavelength. It is, in colloquial terms, when they first came out, people said, oh, you're seeing heat. So infrared somehow became synonymous with heat, but actually visible light is hotter than infrared. So that's a term that technical people stay away from. The infrared is a certain spectral band. The heat can be generated by any photon that you're set up to absorb.
Well, you know, when we sit under one of those heat lamps,
Yeah,
they're what wavelength are they putting out? Is it infrared or are they?
You can look at those heat lamps and you can see that the coil there is kind of a red hot. So it's putting out red and infrared. Incandescent puts out, you know, we don't use those lights anymore so much, but they, a non-politically correct joke just passed by my mind, but they don't, incandescent bulbs put out most of their energy in infrared and only a little bit in heat. And that's why they're so inefficient and so poor to use when you're trying to save electricity.
Right. So again, Tim has another question. Says he was asking about the Pauli exclusion principle. Let's see, what are we talking about there?
For fermions, not bosons, but for fermions, fermions cannot, two fermions like two electrons cannot have the same quantum number as each other. For example, they can be in the first electron shell, they can be in an orbital, and they can have spin up, but the next electron in the same orbital has to have spin down. And so they don't have the same quantum numbers. If you tried to put two spin up electrons in the same orbital, they wouldn't go. It doesn't happen. They will repel each other. So that's for fermions, and that Pauli exclusion principle applies. You cannot condense everything into the ground state if they're fermions, but you can if they're bosons. And so that's what superconductivity is the collapse of bosons to one single state, the ground state. And you get these amazing properties like superfluidity. And if they're charged like electrons, then you get superconductivity. Now, I just said that fermions, electrons can't condense into that state. But what they do in superconductivity is they make an electron-electron pair by exchanging a phonon. And so they act like a charged boson, a negatively charged boson. And those particles can collapse into the ground state, and they become superconducting then.
We're going to have to explain that phonon again. I don't think I remember how
that's a particle of sound.
Okay, so that's how they can exchange through sound. That's
yeah, they shout at each other. I can explain that in simple diagrams too for you.
And that the Pauli exclusion principle is what kind of holds up white dwarf stars.
Right.
And that's for electrons, I guess, there. And then for neutron stars, that's the Pauli exclusion principle for neutrons until gravity overcomes that.
Well, I don't think neutrons are a fermion. They're a boson, I think, aren't they?
Okay. Well, what is it that it's a similar exclusion principle. It holds up a neutron star against gravity.
I think that's the weak atomic force, isn't it?
I don't know.
The white dwarf is definitely held up by the Pauli exclusion principle for electrons. It's basically an electron fluid.
It's interesting how Tim wrote Pauli. He put in Pauli, P-O-L-Y, and actually it's the guy's name, Pauli, P-A-U-L-I. I just remembered that. I was trying to figure out what Pauli was, and I remembered.
Did you see the picture? I sent you a joke about Niels, was it Dirac?
Yes,
Oh no, Planck. It was about Planck, right?
Planck and
before
The hairy
quantum,
topic.
quantum
Yeah.
mechanics. Yeah,
Yeah, I'll go to that. Hold on for a second.
before, during, and after.
right.
Yeah, hold on. Here we go. Let's see. Share that.
Yeah, this is Max Planck before the discovery of quantum physics, during the discovery of quantum physics, in which he played a key role, and after the discovery of quantum physics. You see, it takes its toll.
It's hard to imagine it. That's all him right there.
Yes, and in the 60s, when I took a class from Richard Feynman, he made the statement that he didn't think that there was anyone living that or on Earth that understood quantum mechanics.
And I think it was Niels Bohr that said, if you think you understand quantum mechanics, then you don't.
Yeah. And a friend of mine who we know, Paul Norton, he said you can safely disregard everything you hear after the phrase, according to quantum mechanics.
So Tim has some other questions here earlier, comments. One he says about for planetary nebulas, there's a book called Cosmic Butterflies by Sun Kwok, Kwok, last name. Cosmic Butterflies. So evidently that might be a good one for looking up planetary nebulas.
It has a lot of nice pictures of planetary nebulas and an exposition about them.
Now, there's another book by a guy from the Central Coast Astronomical Society, Kent Wallace. And his hobby was, he has a 20-inch f5 Dobsonian, and his favorite topic is planetary nebulas. He's written a book, but there's no pictures in it. It's all planetary nebulas, and it's his visual impression of them. So it's a limited edition, but it's an interesting book.
Cool. Tim also mentioned going back further to the Owl Nebula, that he had a kid tell him one time that it was a bat ray.
That's the Owl cluster then.
Yeah, the Owl cluster.
Yeah.
Owl clusters. Yeah, not the nebula. Owl cluster. Sorry.
Well,
Yeah.
the bat ray is also often Aquila the Eagle. Looks like an umbrella or a bat ray, depending on how you connect the stars.
Oh yeah, by the way, this picture
ahead,
behind me is M33.
That's the low surface brightness galaxy. Yeah.
But it's fairly dim. This is a long exposure, hours. Okay, go ahead.
What was I going to say? Oh, don't think we mentioned about the Owl cluster, that it's also called the ET cluster for extraterrestrial. Yeah, because I think ET had big eyes. Is that why? I think,
and the outstretched finger that had a glow on it. So that's for one of the wings.
Oh yeah.
Okay.
Okay.
So I think we've reached noon time. So I guess we could probably call it here. What do you think?
All right.
Yeah, I think so. I think we limped along. We missed the Baron.
Yeah, Baron and Tom had problems getting back in too as well.
Yeah.
I think tried to admit them twice. So hopefully you can work on that. We'll have to test during the week, maybe do a test.
You might make a map of the screen that on Baron's computer, screen capture of it while this show is going on, while he's on Zoom. And then you can point an arrow at each of the features that it shows on there and then write in what that does. Press here to get your sound on, press here to unmute, press here to get your microphone changed.
Yeah, I think
I just realized I probably could have just called him on the phone and talked to him that way, but
yeah.
Oh well, too many communication methods.
Yeah.
You were saying up arrow to him. I think he was thinking it was the up arrow on his keyboard.
Well, there is a share screen that's an up arrow.
Yeah, good point.
Yes.
All right, folks. What do you think, Jerry? Call it quits for today?
Yeah. Yeah, we'll see you all next week.
All right.
All right,
thanks,
good
everybody.
show, Jerry.
Good
Well
night.
done. Bye, Chuck.